Thank you all for sticking around for the last session of the conference. So I'm going to tell you about some of our work looking at the ultrafast coherent dynamics and interactions in 2D semiconductors, and very briefly, if I've got time, on some of their heterostructures. But before I get started, I wanted to acknowledge the people who did a lot of this work, in particular Jack Muir in my group, former student in my group, is now at CSIRO with James, and Mitch Conway and Stuart Earle, also in my group. And then collaborators at ANU and Monash, who provided us with samples that we're looking at, and also at Monash and RMIT provided some of the theory support. Now, really, this is a story about interactions. And obviously, interactions are crucial or important for all of the quantum technologies that we've been hearing about over the last couple of days. But even more broadly than that, interactions are responsible for the macroscopic properties and functionality of pretty much all matter. So what do I mean by that? What sort of things are we talking about and thinking about? There's a huge range of things, ranging from, for example, energy transfer, like we've heard about in terms of light harvesting. It could be energy or electron transfer using, making use of the Coulomb interaction or exchange interactions. Or even going to metals and how electrons flow through metals. If it's just the interactions between the electrons with each other, or interactions between electrons and phonons, which ultimately lead to the resistivity. But then if we look at that a different way, these interactions between electrons and phonons can also lead to superconductivity in a BCS type case. Then if we go to, say, for example, strongly correlated electron systems, like our cuprates, for example, then we get a whole lot of different competing interactions on similar energy scales, and a slight change in the balance of those interactions leads to vastly different macroscopic properties, and we end up with this hugely complex phase diagram here. And so in my group, we're looking at all of these, or have looked and are looking at all of these different types of interactions and different types of systems, and for example, in these cuprates, trying to disentangle all of these different interactions. But today I'm going to tell you about some of our work looking at monolayer semiconductors, and in particular, tungsten disulfide. So I'm not going to go into all of the details of these materials and why they're interesting, but basically the key points for understanding what I want to talk about is that these are direct gap semiconductors when you exfoliate them down to the monolayer version. And in this hexagonal Brillouin zone here, we have two degenerate points at the K and K prime, or K and minus K points here, which is where the direct band gap is. And these different points are essentially time reversal symmetric pairs of each other, and have opposite spin orbit coupling, which basically ultimately, the key point for this talk is that ends up meaning that we can selectively excite excitons at either of these values by controlling the polarization of our light. So with a left circularly polarized light, we can excite an exciton in the K valley, right circularly polarized light, an exciton in the minus K valley. Now, the technique that we're using to quantify and to measure these interactions is multidimensional coherent spectroscopy, or you might also know this as coherent multidimensional spectroscopy, or 2D electronic spectroscopy, or 2D Fourier transform spectroscopy. But either way, the basic idea is that this is a phase-sensitive transient four-wave mixing type experiment. So where we're sensitive to the third order susceptibility of our sample. And the way that we do these measurements is that we have three laser pulses from our sample, which are from our laser, which are exciting the sample, and we can control all of the delays between these. And then because then we have a fourth pulse, which allows us to measure the phase of our signal, so through an interference between our signal and our local oscillator, giving us the amplitude and phase of our signal, which means we can then Fourier transform our data with respect to any of our delays, and so generate, for example, a two-dimensional spectrum or a three-dimensional spectrum. And so these are sort of what we're going to look at. So this is an example of a two-dimensional spectrum from tungsten disulfide. And again, the reason we really like this technique is because it's really great at measuring and identifying interactions. So you can see there's a whole lot going on here in this two-dimensional spectrum, where on the vertical axis, we've got what is effectively our absorption energy, and the horizontal axis, what's effectively our emission energy. So you can see we're correlating absorption and emission. And so my plan for the rest of this talk is essentially go through this spectrum and pull apart the different pieces of it to show you how we can get an idea of different types of interactions. Starting with this brightest peak here on the diagonal, which arises, so obviously got absorption and emission at the same energy. This is arising from our A exciton in our monolayer tungsten disulfide. So the location of the peak in general tells us a whole lot of information, but also the shape of our peak tells us a whole lot. So you can see this peak is elongated along the diagonal there. Along the diagonal, that is a result of inhomogeneous broadening in our sample, but what we can get across the diagonal is our homogeneous line width. So even though in this sample we've got significant inhomogeneous broadening, we can still get our homogeneous line width, or in other words, our decoherence time. Now, why is this important? Because our homogeneous line width, or our decoherence, is very sensitive to interactions. And in general, our homogeneous line width is dependent on sort of a radiative recombination or radiative lifetime. We also have exciton-exciton interactions and exciton-phonon interactions are sort of the three things which tend to typically dominate our line width here. And so what we can do is, say, vary the intensity or the fluence of our laser pulses and measure how this homogeneous line width varies as a function of fluence. And from that, we can quantify our exciton-exciton interaction strength. And you can see we get slightly different values if we do these measurements at 6 Kelvin or room temperature for tungsten disulfide. We can also vary the temperature, and again measure our homogeneous line width as a function of temperature, and quantify our exciton-phonon interactions. And in this case, we can pull out interactions with acoustic phonons, getting an interaction strength, and also our interactions with an optical phonon, quantifying that interaction strength, but also quantifying the energy of our optical phonon, which agrees with what we can measure in Raman-type measurements as well. Now, there's also peaks off the diagonal, which again tell us about interactions. And this, starting with this peak here, this cross peak, so we've got absorption again at our A exciton energy, but our emission or our signal is coming out at a slightly lower energy. And where this peak comes from is from a bi-exciton type pathway. So now we're looking at as sort of what is effectively an excited state absorption type pathway. So we're exciting into our exciton state and we're going up into our bi-exciton state, and the emission of our signal that we're seeing is slightly lower than our exciton energy as a result of the bi-exciton binding energy there. So the difference between these is our bi-exciton binding energy. We can also play around with polarization, and because the ability to excite our bi-exciton requires opposite circular polarization, because our Pauli exclusion principle effectively prevents the formation of a bi-exciton if we've got our electrons in the same valley. And so we can see if we have co-circularly polarized pulses, this cross peak here disappears, but if we alternate the helicity of our pulses, then we get our bi-exciton back there. There's still some ambiguity in these measurements, but one thing we can then do is change the ordering of our pulses, and I won't go into too much detail, but basically with this pulse ordering, we can excite a coherent superposition now between our ground state and our doubly excited state here, or our bi-exciton state. So that allows us to directly measure the bi-exciton. And again, playing around with the polarizations, you can see that with co-circularly polarized pulses, we just have this 2-exciton state, unbound 2-exciton state, but then if we alternate the helicity, then we can see we get this bound 2-exciton state there. So we're directly measuring the energy and the properties of that bi-exciton state. Up here, you can see there's a whole lot of things going on up here, and collectively all of these peaks basically come about as a result of the interactions between excitons and electrons that are doped in our system here. Now, in tungsten-based TMDs, the band ordering is such that there's actually a lower conduction band, which is not optically accessible from this highest valence band, but this is where our electrons are going to sit. So the electrons that are doped in our system are sitting here, but that means that when we create an exciton, so if we're exciting with left circularly polarized light to create an exciton in the K valley, we can then form a bound state between our exciton and electron, known as a trion, and there's two different types of trions we can form, either with a spin singlet type configuration or a spin triplet type configuration. And these are split by around 7 millielectron volts, which is what's giving us the multiple peaks here. Now, in a few body picture, we can think of these as trions. In a many body picture, we need to look at this sort of as more like a Fermi polaron. So we have our sea of electrons, which are dressing our exciton states. But for the purposes of this and for keeping it simple, I'm just going to refer to these as trions for now. So To understand, though, you can see there's quite a mess of what's going on here. So to try and disentangle all of that, we can again play around with our polarization. And what we see is if we go to our co-circular polarization, we can only see these peaks on the diagonal. And looks like there's only one peak, but actually there's two peaks that are overlapped there due to the inhomogeneous broadening. If we go to our cross-circular polarization, so again, we're alternating the helicity of our pulses here, you can see that we no longer have the peaks on the diagonal at all, but we've got all of our cross peaks there. So we can go through and map out sort of what interactions between which of these different trion states can lead to each of these peaks. And I won't go through all of the details there, but basically we can see just from these selection rules that we only observe these peaks, we're only observing interactions between the trions when the electrons have the same spin, so when those doped electrons have the same spin. I won't go through the details of sort of the explanation of where that comes from, but basically it comes from a phase space filling type effect where which essentially results from the Pauli exclusion principle, where we can only see the interactions, we'll see strong repulsive interactions when we've got the electrons in the same Fermi seed. You also notice that these two other peaks here, again, I'm not going to go into details, but basically what these originate from is from what we refer to as a bipolaron or a charged biexciton, so where we have two excitons and an extra electron, or the Fermi sea of electrons addressing that state. Okay, so just very briefly, I want to mention that we've also started looking at heterostructures, and there's a huge range of things we can do with heterostructures and changing them, changing the different materials, changing the twist angle, which leads to a whole range of vastly interesting properties, including, for example, simulating some of the strongly correlated electron states, like our Mott insulated or even potentially superconducting states. But to start off with, what we're looking at here is this molybdenum disulfide, tungsten disulfide heterostructure. And the band alignment of these is a type 2 band alignment, which basically means that we can form interlayer excitons. So the highest valence band is in the tungsten disulfide, but the lowest conduction band is in the molybdenum disulfide, which means the lowest energy state is this interlayer exciton here. And so if we pump in the tungsten disulfide, we get electron transfer to the MOS2. If we pump in the MOS2, we can get hole transfer to the WS2. And so in our two-dimensional spectrum now, you can see that we've got sort of our peaks down here, which are corresponding to our tungsten disulfide, our peaks up here corresponding to our molybdenum disulfide, and these cross peaks here, which is corresponding to interactions between our excitons or between our MOS2 and WS2 excitations. And in particular, what we're looking at is then we can then vary the delay between these second two pulses here and look at how our two-dimensional spectrum evolves. And in particular, we're looking at how these two peaks evolve. So we can measure the rise time of this peak here to get the timescale for our electron transfer, and similarly measure the timescale or the rise time of this peak here to give us our hole transfer. I won't go into the details of those results again because I'm out of time, and I'm just going to finish up there with sort of a, again, the point I want to leave you with is that this multidimensional coherent spectroscopy is really ideal for revealing and quantifying interactions. We can do this quantitatively. We can also reveal and identify interactions, which we're now working on towards looking at how we can quantify those interactions. And then in our heterostructures, these initial results have sort of shown us that we can identify these charge transfer behaviors, which are happening on a 40 femtosecond timescale, where we've got where we require a change in wave vector, but on a sub 20 femtosecond timescale where it's direct in k-space, even in the cases where we've got a spin flip, which is telling us something about the spin-orbit coupling in these systems, we believe. And I'll leave it there, and thank you for your attention.
Fantastic talk, Jeff. Maybe time for one question. At the front here.
Okay, so maybe, I'll ask a quick question. So I saw at the beginning of the talk, I'm over here. Yeah, we were breaking down the influence of the different possible types of interactions based on the different rates that you have, and you have a sum over 3 different rates, so to say. I don't know if we can go back to the slides, but I kind of have that picture in mind. And I totally agree that would be the case sometimes, but it's not maybe always the case, right? Sometimes if we start from a Hamiltonian picture, our rates, the coherence rates, the relaxation rates, won't just simply add up like that. And so I was wondering if you guys also have solutions for those kind of more, let's say, more complicated scenarios where you cannot just simply represent a rate as a sum of rates.
Yeah, that's a good question. It's not something we've looked at specifically, but I'd certainly, we typically do essentially build up sort of a huge array of data where we can so vary the excitation density and the temperature and sort of get a complete map of that. In these cases, what we've been looking at, yeah, it's relatively simple where they do add up. But yeah, I take your point that.
Yeah. No, that was not to diminish the talk.
Yeah, no,
and I find the technique amazing. So,
yeah, I guess. Yes, it's not something we've thought about, but yeah, it would be interesting to think about that. Yeah.
Thanks. It's a good talk. I will be very quick. So for the heterostructure, do you think you can also control basically the doping density, the Fermi Fermi energy, for example?
So, in principle, yeah, and so people have done that sort of with gated structures. The samples we've looked at don't have gates on them at this stage. It creates extra complexity and sort of ultimately shrinks down the size of the area. And so generally in the way that some of the necessities of the experiment means we've got a fairly large lot of overlapping spot size there. So that limits it, but absolutely that's something that I'd really like to do.
Thanks.
Yeah.